In a prior chapter of the series, I demonstrated how you can use an ultrasonic sensor with a satellite modem for stage monitoring of remote locations. The agency that I work for is actually piloting some of these systems to measure discharges from a stormwater detention feature in southeastern Arizona. We're also piloting these systems to measure the stage of a spring-fed pond that is subject to flooding. In this case, we're interested in seeing if we can realize an advanced warning system for flooding of a downstream road crossing. In this video, I'll summarize the hardware, wiring, and code for these pilot systems. And I'll also share some video, photos, and notes for these two particular installations. On that note, let's get started. We'll start with an Adafruit Pro trinket, which we will use to drive the ultrasonic sensor. The ultrasonic sensor I'll be using here will work fine with either a 3-volt or 5-volt microcontroller of your choosing. You may also consider adding an OLED display to help you with debugging when your hardware isn't tethered to your laptop. This is not required for successful deployment, but it's definitely nice to have in order to easily confirm telemetry when you deploy. For my circuit, I've selected Adafruit's OLED Featherwing, which provides a nice compact bright display and can be driven by a Pro trinket. If you decide not to use this OLED, you can edit out references in the code and the wiring diagram. The following screenshots demonstrate how you will wire the OLED to your breadboard and Pro trinket. This shows where to attach power, and this shows how to attach the display to your microcontroller so that it can be driven using I2C protocol. And this is the ultrasonic sensor I'll be referencing. This sensor comes in a nice weatherproof enclosure which is perfect for outdoor field deployments and is relatively accurate with a resolution of 1 centimeter. And here are the pinouts for the sensor. I've highlighted those pins that we'll be referencing in both our wiring and our code. For this sensor, the manufacturer also suggests adding a noise filter on the power supply, so we'll include that in our wiring diagram as well. As a side note, additional details including sensor range and accuracy have been summarized by my colleague Carl Hooper, who works for Cochise County, so thank you, Carl, for your support on that front. With his permission, I've included links to the documentation he's prepared in the description of this video. So here's the circuit for our microcontroller driving the ultrasonic sensor and OLED display. And for those of you interested in remote monitoring capabilities, here is our satellite modem added to the mix with respective pinouts highlighted in code. As mentioned in prior videos, if your deployment will be powered by a 3.7 volt LiPo battery, I recommend purchasing the 9603 modem rather than the naked MK2 or 9602 modem. The pinouts will be the same, but you will need this color-coded accessory cable manufactured by SparkFun to work with the wire harness on the modem. And this shows how you will wire the respective color-coded wire harness to the Pro trinket to work with the code I've provided. The code referenced in this chapter will build on the chapter entitled Remote Flow Detection Through Satellite Telemetry. If you need a deeper dive into the code I'm providing, please consider reviewing that chapter, since this chapter will only highlight changes associated with incorporation of the ultrasonic sensor. And as always, all the code shared via this channel is licensed under Creative Commons and available via the website identified in the description of this video. I'd recommend reviewing, at a minimum, the code summary in Chapter 19 as a foundation for the next slide. The major changes to the satellite telemetry code already shared will include these two new functions, which will engage our ultrasonic sensor for a range reading and then calculate the change in range over time. We can then look at that measured change in range and consider a threshold for determining if telemetry should be initiated between our standard telemetry intervals. In this version of the code, I have that change commented out of the conditional. If you do this, the sensor will just report telemetry on your time interval frequency. If you uncomment this, make sure that you set a reasonable number for your change condition to be referenced in that conditional, and that number is going to be in centimeters. If you set this number too small, you might trigger rapid telemetry in response to environmental conditions that you aren't really interested in capturing, and that can unnecessarily drive up your telemetry costs. Until you understand what your field conditions require, keep your change condition commented out of the conditional. Finally, if conditions are met for telemetry, your field data will be transmitted to the Iridium gateway, which in turn can be configured to relay respective field conditions to your Internet of Things website. This is a historical photo taken in 2015 of major head cutting moving up a valley in southeastern Arizona. This is a challenge for us for many reasons, ranging from loss of grasslands to contributions of sediment in stormwater. Suspended sediment is correlated to high E. coli in the water column, which can contribute to downstream water quality impairments in receiving water bodies. A stormwater detention basin was constructed to give an opportunity for stormwater to spread and infiltrate before continuing on its path to the San Pedro, hopefully with sediment and E. coli attenuated prior to discharge. In order to measure the water quality impact of this feature, we need to be able to collect samples upstream and downstream of the same when it's flowing. But rainfall in Arizona can be very intense, localized, and short-lived, and making trips to these sites can be resource intensive. So how do we know when there's stormwater to sample? And this is where our remote environmental monitor can help. We decided to install one of these with an ultrasonic sensor at the outfall of the basin to help us receive notification and respond to stormwater events efficiently when they occur. This pilot installation was spearheaded by one of our interns, Sean Keene, who was also responsible for modifications to our original REM code to work for this particular application. We learned a lot from his contributions, and as you'll see, this was a very good pilot. But we've also realized a few challenges that we can learn from moving forward. So we lost field audio on some of these clips, so I'll briefly describe them. I'm standing in the basin now. That's where the stormwater is going to exit out to Horseshoe Draw. That's the basin berm. And now I'm looking upstream at where the water is going to come into the basin. And this is the hardware, a 1-inch galvanized pipe that Sean put together before we came out to the field. You can see the ultrasonic sensors attached to the end, and he's fed the sensor cables through a conduit through the inside of that 1-inch pipe. And we'll simply just feed that through a watertight fitting into the bottom of the REM, and then attach the REM to the retaining wall. And this shows where the culverts exit on the downstream end, and you can see that there's standing water in a pool that's lined by a rock apron, and Sean is basically determining where he's going to hang that sensor on the side of that retaining wall. Here we're trying to determine what depth to set our hammer drill to have a little bit of that wall anchor bolt sticking out so that we can bolt that a galvanized sleeve to the same. And you can see that Sean now is tightening that galvanized sleeve to where those bolts were inserted. And now he's going to go ahead and take the conduit with the sensor, and he's going to feed it through that sleeve.
It's a good thing we're not threading a needle or something. So you want to go back up the threads, right? Mm-hmm. And then we want, that looks pretty good right there.
And you can see here that Sean is mixing up some JB weld, and he's going to apply that JB weld to that sleeve to help us secure that galvanized pipe a little bit better within that sleeve, although it will be anchored down. But really we want that nice and tight and level so that ultrasonic sensor functions properly as designed and installed.
Yep, right there is good. It's level.
Okay. You like it? Is that level? Pretty well?
It's pretty good. Oh, I didn't know this was magnetic. It's actually really good.
Okay, awesome.
Okay, looks pretty good.
All right, so we're going to replace the angle watertight fitting with this straight one, and then we're going to mount this on the retaining wall. And it's not ideal but it should work in Arizona. This thing's going to be in the shade for a big chunk of the day, but we have so much sunlight out here, it should be okay.
That's right next to the edge. This doesn't seem very secure to me, but
Had a little problem. We drilled our holes too big for the anchors, so we went ahead and we used some masonry screws with some JB weld, and it seems to be holding it in place pretty well. How's that holding up, Sean?
Yeah, it's solid. It's not going anywhere.
And we also did the same on the pipe and on the thread for the ultrasonic to keep that from moving. And it's a good thing that Sean thought of using galvanized pipe. I used PVC originally, and obviously PVC is it's not gonna hold up to the elements as well. It's gonna shake in the wind. This stuff looks pretty stable to me, so that was a good idea.
Okay, so I'm just gonna plug the solar lipo charger into the trinket. Everything else should be plugged in already.
So what's the depth on that?
We're about 5 feet and 4 inches from the dowel to the water level.
Okay, so it's about 5 feet and 4 inches in case my mic didn't pick that up.
Yeah, I'm gonna go look at it on ThinkSpeak. So the text doesn't show me any of the data though. I have to go onto ThinkSpeak to look at that.
Okay.
So
So you were able to get on ThinkSpeak then?
yeah, so we got onto ThinkSpeak. We measured it as 5 foot 3 inches down there, and we are reporting 159. That would be centimeters as the stage level, which turns out the conversion 62.59 inches. So within a half an inch of accuracy on the rangefinder down there.
And it's pretty stable too, right?
Yeah,
it's
it's
not jumping around.
No, we did have a jump on the last one just up to 160, but it's 159, 159, 160.
That's
on,
awesome.
on the last 3.
So that's great.
Yeah, and then we got our battery voltage too, slowly increasing with the Arizona sun.
Perfect. So here's some data reported by our remote environmental monitor downloaded from our Internet of Things website. Here you can see periods of evaporation of water stored in the small rock apron basin downstream of the outfall, as well as these discrete flow events, which was causing the elevation in that small basin to rise. We did have a period when our subscription to RockBlock expired without follow-through on our end, resulting in this data gap. But overall, we managed to measure a total of 4 flow events between November of 2018 and May of 2019. Starting in April, we began to witness increased telemetry frequency resulting from our telemetry conditional responding to frequent changes in range. This was driving up costs significantly, and we weren't sure if this was due to cattle walking under the sensor or something hanging under the sensor, if it was some other hardware issue. So we temporarily terminated the service until we could get out there and see what's going on. So one hypothesis is that when the downstream basin dries out, the exposed rocks are causing the ultrasonic signals to reflect at odd angles. This in turn is impacting the measured change in elevation, thus tripping our telemetry conditional. This makes sense since we didn't have this problem until the basin dried out with a reported range of about 200 centimeters. And this is one of the challenges with this site is the roads can get washed out pretty easily, and we don't want to risk getting stuck out here. We also don't want to damage the road. So this can pose some challenges for sample collection out here. Okay, so I'm approaching the spillway for Horseshoe Draw. You can see some of my colleagues out there. So this is Horseshoe Draw where it comes out of the spillway. as well as the culverts that we're monitoring. Okay, so we just arrived at the site, and it looks like things have held together pretty well. A little dusty, but overall, looks pretty promising. So you can see this little retention basin downstream of these culverts is full of water right now, which is exactly what we want to see. The water provides a nice smooth surface for the ultrasonic signals to bounce off of, but you can imagine that when this water evaporates, that's the material that we're trying to measure, which is causing all kinds of problems for us. I was planning on installing a couple tiles, some scrap wood. I brought a level to underneath the sensor to see if we could create a nice smooth surface for when this thing dries out, at least temporarily, until we can come up with a more permanent solution, but I don't think that's going to happen today. Okay, let's see what we got. Ooh, I feel some moisture coming out of the bottom of this thing, which is never good. Things are pretty wet and moldy in here. So I'm seeing that the foam that was used as a foundation for mounting the electronics is growing mold, and there's a lot of moisture. Okay, so here's the original battery. It's got a lot of moisture on it. I brought a new battery to replace the old one with, and I also brought a new pack of silica gel, although I think I'm going to need something a little more substantial for these conditions. All right, so I went ahead and I plugged in a fresh battery, tried hitting reset on the Pro Trinket, and I don't see any lights or any response. Part of the problem is I have this little lipo charger backpack that was originally installed in this design that's covering up the LED. So I figured maybe I can't see it, but I did reset this, and I'm getting nothing on my phone, no response at all. So there are a lot of lessons to be learned from this installation. Coming back to this, I think we want to avoid using those little lipo backpacks for the batteries on the Pro Trinket, because it obfuscates the LED display. I am seeing the solar lipo charger actually does have a light that's coming on, indicating that it hasn't been damaged by all this moisture, but I can't speak to the rest of this setup. So definitely in a situation like this, where the box is sitting over standing water like it is here, we need to come up with a better design, because moisture is definitely a problem here. Okay, so I'm going to check to see if this thing is loose. Yeah, it's moving. So you can see the problem here is that even though we put some JB Weld in this sleeve, it didn't really hold up to the elements. So that's something else we're going to have to revisit in terms of trying to improve this installation. All right, so I went ahead and I removed most of the equipment that was inside the box. I'm going to have to take this back home and test it. This was one of our older designs. It's we've made a few improvements in the way we build these now. So we just need to revisit this. I don't consider this a failure. I consider this a learning opportunity on how to do this better. So here's another example of an ultrasonic sensor coupled with a remote environmental monitor for monitoring stage from far away. In this case, we'll use the REM to monitor a fish pond on Spring Creek. When this feature floods, the Forest Service wants to be notified to ensure downstream road closures for public safety. The challenge for this location is that we have an uneven rock face that we need to anchor to in order to extend the box and sensor out above the water where it can take measurements, receive sunlight for charging, and have a clear view of the sky for satellite telemetry. Thanks to recommendations from friends at a local hackerspace, we used a conduit junction box anchored to the rock face with 1/2 inch conduit, thus giving us a means to extend our REM away from the rock wall. This is a summary of the connections, which can be picked up from your local hardware store. We initially attached this fitting to the back of our REM using JB Weld. We did this because we didn't want to drill into the box given the possibility this might provide a path for moisture. For our Arizona conditions, we learned that JB Weld may not be the best alternative for load-bearing applications. This became apparent when we started receiving odd measurements from our box, and upon revisiting came upon this. We were lucky that we had wrapped the antenna wire around the conduit several times, which prevented us from losing our box. We determined it's safer to screw this hardware directly to the box from the inside and then follow up with a bead of silicone. Upon doing so, make sure the threaded female section for this junction is facing upwards on the box. This will be important for mounting our antenna, as you'll see shortly. Also, make sure you use a longer junction to facilitate some elevation above the adjacent solar panel. Since this was another pilot, we hadn't yet figured all this out when this particular photo was taken. As far as mounting, we once again have to thank our friends from our local hackerspace for the loan of this Remington tool, charges, and nails, which was perfect for securing the junction box to the rock face. With a little bit of practice, we finally got the junction box attached to the rock face. Since the rem on the other end of the conduit is acting as a lever, we did place a shim under the elbow to prevent the box from moving in response to this clearance. Again, these were all things that we learned in the field, where conditions can draw your attention to new challenges not visible in the office or lab. Once the rem was installed, we then applied some JB Weld to the top of that junction fitting and attached a washer as a magnetic point for attaching our helical antenna. The cable from our antenna was then threaded through the watertight fitting and attached to the modem. And here's the antenna attached to the washer via a magnet that's embedded in the bottom of this antenna. We made sure to level things out, which was fairly easy to do with gentle pulls on the conduit. And also made sure the ultrasonic sensor was perpendicular to the water surface by simply loosening the conduit lock nut, turning the box, and then tightening it once again. We then measured the range and reset the rem to test telemetry.
Alright, so we're going to run a quick test on this. I just reset the trinket, and I'll just read off what I'm seeing in the OLED. It says rem setup, let's test connection. Stage level is 141 centimeters, and we'll compare that to our measured height in just a second. And now it's sending message to test connection in the loop. It's talking to the rock block, so it's got to wake up the rock block. So this is just going to take a few seconds. There it goes. So that red light right there means that the rock block is on, rock block turned on. It took another stage reading. It gave me a string. Message sent. Setup complete. Turn off OLED with on-off switch. So we're going to turn off the OLED and we're done. We can close this.
And here's the data reported to ThinkSpeak over the course of our first month, showing little variability at this time. I should emphasize that I'm not an electrical engineer. I've been exploring this technology in the hopes it can help my agency accomplish more environmental good with fewer resources. Along those lines, all constructive comments and recommendations are most welcome. Thanks for watching, and please subscribe for updates.